Thank you. Thank you very much, Professor Judy. So it's a pleasure to speak here at the University of Michigan campus, and especially double pleasure to see my former colleagues, Dr. Hyde, who is also a professor here now after Ford. So therefore, the title of my talk is here on the page. I'd like to say that I would like to make, as much as I can, I would like to make the connection to the manufacturing research, although this is less to do with manufacturing as far as the active manufacturer is concerned. But it's still related to the manufacturing, as in when we receive the feedback from the field, when we get the failures coming from the field, and we can classify them in a design-related or manufacturing-related issues. So this talk is primarily around the statistical models that we are using in order to make some meaningful inferences into the engineering domain, including, like I said, either manufacturing or design space. So, the talk is called Recurrent Data Analysis in the Framework of a Socket Model. So let us first, the first few slides of the presentation will be devoted to some introduction into the material. See, I have to explain some basic models for you guys. And I understand most of you have the engineering background for sure, but how many of you have took courses in reliability or applied statistics? Anyone? Statistics, right? Yeah. Okay. Okay. Well, then I'll try my best to explain on the fly as we go. But what's a socket system? A socket system is, well, first of all, we have to distinguish between the so-called non-repairable and repairable systems, right? Of course, non-repairable is a self-explanatory, intuitive type definition. That is, upon a failure, if this component fails, it loses, 100% of its functionality and can be brought back to the operation only by a full replacement of this component, right? As opposed to a repairable system, if it's a huge system and something gets wrong with the system, you can fix the system and release that same very system into the operation without replacing with a brand new system. And you see, and these two approaches in, this categorization into repairable versus non-repairable then corresponds to the respective statistical models that you will be using to analyze this. So for example, a socket system, and you will see later in my in my presentation that I'm using a case study of an engine with spark plugs. I think anyone can imagine a regular internal combustion engine which has 4 or 6 or 12 spark plugs, right? So therefore, if I draw my boundary around the engine itself, then to me it's a repairable system, just because when any component within the engine fails, I could hypothetically replace that component and return the engine back into the operation, right? At the same time, if I draw my boundary around the spark plug, individual spark plug that fails, then it's a non-repairable component, because very rarely do we repair spark plugs. So I would just throw them away and replace with a brand new spark plug. So therefore, the socket model is such a system where it's a repairable system, but the process of returning it back to the operation is in effect that you're like in a socket. You're pulling out a component and plugging back a new component. Okay. So now, when I'm analyzing, and imagine that now every unit is a separate vehicle, right? And then there are multiple failure events for each of the units, and even assuming this, by the way, this shock loss could be one and the same component failing or different component failing, right? Components failing. So for the sake of simplicity, let's assume it's one and the same component failing. So looking at this data statistically, we can analyze this data from 2 angles. The first angles, if I concentrate on the so-called times to the first failure. In other words, if I'm really interested in the component level reliability, I will collect all this time to first failure. I will probably construct a statistical distribution of those failure times and make some inferences, right? Such as the so-called B10 life estimation, such as the probability of failure estimations, the functional time, etc. But the important conclusion from this kind of approach is that once I collect these failure times from these components and construct the relative probability of failure curve, also known as CDF, as the CDF, cumulative distribution function. The property of this function that it actually saturates at 1. In other words, the number of components that can potentially fail in this scenario does not exceed the sample size, the original sample size. For example, if I had 100 vehicles and on each of them there was only one spark plug, by the time all they will have failed, all I can have 100 failures of spark plugs, right? By definition from this approach. However, if I'm now looking at the same situation from the standpoint of the repairable system, I'm saying, okay, let me assume that any of the system is a black box. And all I do, I'm recording a failure against that black box, no matter why the failure, without analyzing why the failure has occurred, okay? Then from the standpoint of the black box, if I collect all these failures relative to the 3 repairable black boxes and relate them to the number of black boxes, you see that the number of failures can exceed the number of the system in the operation, right? Which then means that my traditional probabilistic model, which is relying on the time to failure distribution, and of course this density integrates to 1. In other words, the area under the curve is equal to 1, right? So this model is no longer good for me to model the repairable situation with the so-called recurrent repairs, right? Because once again, if a repairable system fails, I fix it up and I release it back into the operation, yet, without replacing, without adding a new one, right? So therefore, for me to be, and then of course the expected number of failures per system here saturates to 1, whereas here it can go over 1, it can grow, right? And therefore, I need to use an alternative statistical model to be able to deal with the situation. And this model is, we will see in a second, the so-called stochastic. Yes, sir.
It's the failed element.
Yes.
You have another one there. You replace.
Yes, you have
so
another
now
one.
You can wait the same for the first time of breakdown, and you can have as many measurements as possible. Right? You don't have to go through this additional model. Just assuming that all elements are of the same reliability.
Well, if the same reliability is going to be the so-called regular renewal process, and I will explain. You're right. One particular case is one when I replace every time I replace it with a brand new one, and then I'm actually tracking those replacements as a function of time. I'll show you that model in a second. So now, yes, the so-called underlying the nominally homogeneous population. Yes, yep. So now, let us consider different scenarios under which a component can fail. In fact, this repairable system can fail due to a component, and different options for restoration of the component. For example, if my system starts operating here at time 0, and the failure occurs here at time t0, okay? Then one way to restore my system, again, what's your name again?
Simeon.
So Professor Simeon said that and he's right, one of the ways to restore the system is to replace it with a brand new component, without repairing that little thing, right? So this is called as good as new restoration, and the respective probabilistic model that governs this process is the so-called ordinary renewal process. And we'll see in a second what the process is, okay? Now, the second scenario, if big system fails, such as, I don't know, this TV panel, although I think these days TVs become so cheap that they consider them non-repairable, right? By the time you repair it, it's easier for you to buy a new one. But let's say it's a repairable system, and let's say only small, I don't know, power supply cord failed on that system. So if I take that, TV panel together with the power supply cord as the general system, and I just replaced one power supply cord, then release it back into the operation. Then, in terms of the age of that system, this is the so-called same as old restoration. In other words, I am returning the system after the repair to the same age as it was right before the failure. As opposed to here, I am returning it back to 0. I'm resetting the age of the system back to 0. Okay. And these are, and of course, these are theoretically the two asymptotic conditions. But you guys know that in real life, you could easily have this kind of restoration. In other words, you repair the system in such a way, or you repair such a proportion of that system that it's actually neither as good as new, nor is it as, the same as old. And then Art could attest to that in how many cases we come across with the repair procedures that we deal with this situation after the repair. In other words, during the repair, you are unintentionally introducing the new failure mode that, from the common denominator, so to speak, degrades the system even to the worst condition as it was right before the failure. You know what I mean? Again, if the power cord failed, power cord is a trivial failure, right? But by fixing it back, you did some kind of short circuit, and then your whole power supply fails. You know what I mean? So then, in that sense, you're dealing with this so-called worse than old situation. Okay? So this is just a conceptual scenario. Let's see what happens mathematically. So order renewal process. The easiest way to think about it is in terms of Monte Carlo realization. So, for example, if I have the underlying population of components, nominally homogeneous components, all identical, then when the first component fails after time x1, for me to replace it, I'm actually going to the underlying distribution. I draw another random component of from the same population and replace it, and that second one could fail as the time equal x2, x3, and by the way, you could see that these times are not necessarily, of course, equal to each other, because it's still although it's a homogeneous, the same population, but the failure times have variability, right? So then, what I'm interested in practical purposes, as I'm counting this number of replacement as a function of time, my statistical model, which makes a lot of practical sense, for example, we use it in statistical warranty forecasting. If I can pick up this trend, how my population of car is failing, I can fit a parametric model, and I can extrapolate it over to the future, thus predicting the required warranty budget, which has to be set aside in order to cover for the forthcoming failures. Okay? So now, mathematically, there is a very elegant expression for this renewal process, because after all, the so-called renewal function. So what is renewal function? The two elements. The first one characterizes time to first failure. In other words, when you are dealing with the repair of the system, you will always have to deal with time to first failure before you go into recurrent failures, right? You have to first to fail for the first time only. So therefore, this piece is quite manageable. But then all the subsequent failures, anyone recognizes this mathematical expression in this kind of integral? What is it called? There's convolution integral. This is the convolution integral. And Professor Simeon probably can attest that these are not easy to handle. Especially, usually people use Laplace transform, to translate it into Laplace space, do some algebra, but the inverse is not always easy. For example, in my concrete situation, if my underlying distribution of time to first failure is so-called exponential distribution, that's the only case when I can resolve this integral in a closed form. If this is Weibel, and you know that Weibel is one of the most popular distributions in reliability. By the way, do you remember that in the Russian textbooks they actually called Weibel-Gnedenko distribution? Whereas here, for whatever reason, they dropped Gnedenko. Just Weibel. Well, maybe Russian collusion, or who knows, what's going on. But anyways, the thing is that this convolution integral is a nice expression for renewal function, but realistically, in practical applications, we really have to rely on approximations. There is no closed form solution for the renewal equation for any other distribution than exponential. Okay, and there's I show you a bunch of approximations that people have used over the years. We even came up with our own approximation here using the Padé approach, but approximations work, and therefore I can indeed then fit this solid line into this recurrent process. I can extrapolate it in the future and predict the future number of failures. Okay. So then one particular case of the so-called renewal process is the so-called homogeneous postone process, HPP. The homogeneous postone process is a regular renewal process corresponding to the fact when the underlying distribution is exponential, and which is why that big convolution integral reduces to this equation here, right? Again, if I were to do this Monte Carlo way, what does HPP mean? It means that the intensity of failures over time is constant. It's not degrading, it's not increasing, it's not decreasing, it's constant. And indeed, so in this case, I'm using the exponential distribution with escape power of 25, and I'm simulating MIS, by the way, my common acronym in the automotive industry, Sajid now knows MIS for months in service, right? So how many failures do I expect for a given subsystem for the months in service? And of course, you have to understand this is a fake data set. Ford does not fail that big, over 24 months in service, which is 2 years. No, it's just an educational data set. But the idea here is that if you look across the number of failures, they are random, they're fluctuating, but they're approximately constant. 39 versus 40 versus 42 versus 45, and it's approximately constant. So this is HPP.
The population size not change here.
No, it doesn't change in the sense that it's a repairable system, right? So I'm fixing up and I let it go into... Later in the life, we use the so-called population attrition model, which basically says if I start extrapolating as to as high as 10 or 15 years in service, it's just by natural reasons people get into accidents, people just salvage their cars, and therefore at that point the population will start dropping out. But for my... No. But I'm usually studying one population of vehicles. For example, 2017 model year, I'm interested in the reliability of that one. I'm interested in the warranty for that specific population. You know what I mean? So therefore, if I were to trace it for over a longer period of time, I will have to start applying some... And we do that, for example, our emissions warranty go as far as 8 years. At 8 years in service, there is already a finite probability that attrition may kick in. But over the first, 7 to 8 to 10 years, to 8 years, that probability is still very low. Yes. Yes.
Will be monotonically increasing or almost monotonically increasing or not necessarily the number of failures per month?
It depends on the underlying failure mode. For example, if you're dealing with something like corrosion, fatigue, or something that has a tendency of accumulating cumulative damage as a function of the age, it will be increasing. If you're looking, for example, I was once looking at the reliability of the, what do you call this, jack? When you lift up the car. Screw jack? Yeah, of a screw jack, right? And when I was looking at the trend, it was neither increasing nor decreasing. It was almost perfectly constant. You would say why? Well, on the one hand, from Ford only, right? But most importantly, random Poissonian usage. In other words, you only use it when you get a tire puncture, and tire puncture does not have a trend. A brand new car can catch a nail, and an old car can catch a nail, and therefore so the duty cycle is actually randomly constant. Therefore, the respective failure trend is constant. Okay. Spark plug will be slightly sliding up. It will start as a function of the age. It will start sliding up because for example, if there's a micro crack, that crack will be propagating because of the vibration of the engine, etc. At some point. So therefore, an older spark plug will have a much higher probability of failure than a brand new one. So that was HPP. Now NHPP, non-homogeneous Poisson process. So what was interesting in this HPP is that this trend was approximately constant over time. Now with an HPP, the trend now becomes a function of time. So therefore, and there are two common models to model this, how it increases the function. By the way, it could also be decreasing as a function of time. The so-called infant mortality. Those weak components that are born defective, so to speak, as soon as they enter the field, they fail right away, and the rest of the healthy population just remains with no failure, right? So therefore, it could be either decreasing or increasing. So, and then here, by the way, Professor Simeon, so here you see the increasing trend, right? Remember, those numbers were fluctuating. Here you have 21 going to 28, going to 38, going to 40. So it's really an increasing trend as a function of time, okay? So the final model before I go to the actual application of this, I'm still setting up the scene, okay? The final model, remember how I said when my restoration could be anywhere between 0, i.e. as good as new replacement, and same as old. It could be anywhere in between, right? So there is the so-called Kijima model, a Japanese scientist who proposed this, who introduced the so-called the notion of the virtual age. Basically says, if this is the age of the system right before the failure, and this is the age of the system right after the failure, then this one becomes the so-called restoration factor. To what degree does it get restored? For example, and if Q is equal to 0, it means that the age of the system after the failure is equal to 0. What does it mean? It means a brand new replacement. You just reset it, right? If it's equal to 1, then the age of the system before the replacement is equal to the, before the repair, not replacement. Before the repair is equal to the age of the system after the repair, right? Which means that same as all. Remember how we said small fraction of the system, it means the system has the same age. And of course, by allowing Q to be anywhere in between, you are modeling this better than old but worse than new restoration, okay? And here's the respective G renewal. Remember I showed you a regular renewal function? Now you're looking at the G renewal function, still a convolution integral, but this expression became much more complex, right? Again, no closed solution is impossible, period, now, so for any underlying distribution, okay? And, but numerically, solutions could be developed, using the numerical integration approaches. So now, finally, going what were called practical problem statement, and this was the actual case study where, I'll tell you, there was even legal aspect to this case study because we had a lawsuit with the supplier. Yes, sir.
When I was working in Ford, we had the example like for the headlamp systems, suppose.
Yes, sir.
When we look at the data of the less durability, like 3 months in service vehicles, the warranty count will be very less. But when we see the data for the high durability, like 24 months in service or 36 months in service,
yes,
the data will be increasing drastically.
Yes.
So can we predict those type of failure modes also through this model?
Yes. So that's exactly why they're developed. So the idea is for the model to pick up the trend based on early failures, and then extrapolate the trend reliably into the high time in service. The only problem is that if the early time in service failure modes are only characteristic, it's almost like to human nature, right? So if kids are getting all kinds of, measles, etc., this is considered to be a childhood disease. And things like, heart problems, etc., is considered to be middle age to older age disease. Therefore, I have very little chance of predicting the heart disease just looking at the young population. I mean, I have no information there. I could employ the so-called Bayesian techniques, right? I could rely on some of my prior history, how a similar population behave in the same condition, extract some inferences and impose to this population. But generally speaking, it's so that's the only restriction. But in all other cases, yes, the idea is to pick up the early failures, extrapolate to the high time in service, at least it's through the end of warranty, and then predict the expected warranty budget. Okay? So now, practical problems stated. Like I said, this was a actual case study. Of course, I had to mask all the data due to the confidentiality reason. But here's the case study that comes from this recurrent problem analysis. So, the so-called sibling components, and again, I'm returning back to the spark plugs. So many vehicle components have their siblings, such as, for example, left and right mirrors, front rear doors, head versus rear lamps, etc. Okay? So now, these components are often coded with the same part number. Well, actually, as far as mirrors are concerned, I could have part number, 1067A versus 1067B. At least there I have nomenclature distinguishment. I know that's a left mirror, this right mirror. But things like, the wheels, the spark plugs, and many other components are identical components having the same part number, you see, okay? So then what happens? Therefore, a dilemma arises as to how to interpret a repeat repair coming from the same system. So let's say from vehicle number 1, I recorded 2 or 3 consecutive repairs. But since I don't have related to a given part number, so as I'm looking at the second repair, should I interpret it as a secondary repair of the component that had already been repaired once? Or as the first repair of one of the component siblings. You have to understand this problem. It's important that you understand the problem. Do you guys follow? So if let's say the first time, this is one and the same engine. First time I replaced the spark plug, but I don't know which one. I mean, there was a record in my system, warranty system. Spark plug was replaced with the spark number on this VIN, vehicle identification number. Second repair comes in, and I start puzzling. Hey, is this the same one that I just replaced, or is it one of the siblings that also failed, right? This, believe it or not, this simple dilemma has profound business implications. Why? Because if, in practical terms, it is necessary to understand whether repeat repairs are related to a particular sibling, which might be operating in inauspicious conditions relative to other siblings. In other words, if I can convince myself that, all these consecutive repairs coming exactly from cylinder number 1 in all cases, this tells me about the so-called system design issue. In other words, the part could be okay, but something is overstressing my spark plug, specifically in cylinder number 1, right? As opposed to the case where all these multiple recurrent repairs of the same engine are coming from the spark plugs from different locations. Then it's the opposite situation. It says, nope, the system is working just fine. There's a fundamental problem with the spark plug itself. So we are distinguishing between the so-called component level reliability and system level reliability. And the reason I said it's profound business implications is because we don't manufacture our own spark plugs. It's usually a supplier. So it becomes a finger-pointing game. So that, so it says, Ford, that's your fault. Because you designed the system in such a way that it's overstressing cylinder number 1 consistently. As opposed to them, no, guys. Our design specs are fine, system is okay, but you just gave us a defective plug, which fails randomly at different cylinders. Yes, sir.
So how do you rule out a common cause failure in the sense that, maybe 1111 can be attributed to a problem with the piston, but say it's a problem of the crankshaft, so you're getting random failures, but it's not the spark plug, it's associated with the...
Not easy, the so-called confounding.
Yeah.
It's a classical confounding problem, and for that case, we'll be brainstorming and just looking at the failure frequencies of the components surrounding that, so to speak. Other components in the engine and trying to see if there's any correlation. Okay, but you're right. That could be masking. It could be another factor contributing to this convolution. But still, in many cases, it's relatively simple problem statement. So I'm trying to differentiate between the system level issue versus the component level issue. Okay. So and again, but the dilemma is this stream of failures are coming to me from the system, from the black box called engine. I know related to particular component, I have no idea which one fails, okay? And I mean, it's mostly, I don't know if they're coming from one and the same location or random location, okay? So now, how do I approach this statistically? Now, remembering the theory that we just laid out before. Then, all I'm saying, as Professor Semyon said before, since we're doing the brand new replacements, so this is a case of the regular renewal, ordinary renewal process. Okay, because I'm indeed replacing with a brand new part. Okay, and then if I assume hypothetically, so this is my black box, like theoretically I don't know what's going inside, but let's assume I know, and let's assume I know that in this case now there are 4 siblings, 4 different spark plugs within the same engine, and I know that most of the repairs are coming from one and the same location, i.e. related to one and the same sibling. Okay. Then, like I said, this process that I observe as the output is going to be a regular ordinary renewal process, and the underlying assumption then time to recurrent failures is the so-called IID, independently and identically distributed random variable. So therefore, statistically, my task is to record all these inter-arrival times, time between consecutive failures, and to prove statistically that they satisfy the assumption of that they are A, independent, B, identically distributed. That's number 1. So and then I can conclude, yep, this is, if I can prove that statistically, I can say, yep, this is a system level problem coming from the same location, you guys go figure it out. Okay, why? So now, if now I assume that consecutive failures are coming from multiple siblings, and remember at the black box level, I observe the so-called superposition of several stochastic processes, right? Then it can be mathematically proven that this superposition is no longer identically and independently distributed random variable, okay? So then, if I observe this, and I can, the only thing is that don't think that everything is so easy in the practice. In other words, you cannot just say, I could just look at this visually, I could say they're approximately equally spaced out. First of all, you have hundreds of this, right? So it's just, your eyeballing is not enough. So same as here. I mean, is it really different, or is it about the same, these distances? You know what I mean? But there are reliable statistical procedures that can help us do that. And I do, when I was first attacking this problem, I did find one other research paper, which was coming, by the way, from Iowa State, Judy. Maybe you know Meeker and Escobar. They have a famous book on reliability. Okay, so these are the two titans in the field of reliability. And they co-authored the paper where they also were looking at the superimposed renewal process, at which I'm looking, but they were looking at them from the classification perspective rather than estimate. See, I need to estimate those distributions in order to resolve this dilemma. So in their case, they were, so let's see, consider problem of estimating the underlying problem. Oh yeah. So they were I take it back, I misspoke. They were looking at the estimation problem. They were looking at the superimposed data coming from the black box, and they needed to know the parameters of the underlying distribution which is driving this model, but their case was only this scenario here. Only this scenario when all the data are coming from multiple random components, they are actually looking at the superimposed data and trying to reconstruct the time to the first failure distribution for this data set. In my case, I consider two scenarios, and I would like to be able to distinguish between them. Okay? So testing, how I test for the IID assumption? Well, there is a couple of established tests, the so-called Lewis-Robinson test, which provides the statistic helping to estimate whether or not the a given set of data is identically distributed. I'll show you the numerical example, will be easier to follow. And then the same thing for the independence, you compute the so-called first-order serial correlation. You're basically in a setting of multiple repairable components. You're basically saying, okay, are my time to first failure correlated to the time to the second failure? Times to the second failure correlated to time to the first failure, etc., etc. Okay? So here is a quick numerical example, by the way, related to the so-called single repairable system. See, in the repairable system data analysis, there is this dilemma of studying a single repairable system versus the population of repairable systems. By single repairable system, we mean a system such as, for example, nuclear power plant. It's still a repairable system, right? Because it produces electrical energy from the atomic energy, but it's stationary, it sits in the same location, it has tons of components inside it, and against that system, you can have multiple recurrences. So first time, the power plant is down because of the water pump failure. Second time is down because of the heating element, etc., etc. Right? As opposed to population, multiple repairable systems, like my case, automotive industry. Right? I have a car which is repairable in itself, but I'm selling 6 million of this car a year, of these cars a year, as opposed to one power plant. You know what I mean? So therefore, the procedure is slightly different in nature, and I'll show you the statistical flavor of the difference between them. But for the sake of the discussion, here is the actual here is the plot of the time between consecutive failures. So, by the way, this is cumulative time versus cumulative failures. But of course, looking at the incremental differences, this would be your consecutive failures. And putting this data through this statistic, it tells me that the p-value is non-significant. So what does it tell me? The p-value, it means that the incremental failure times do not significantly differ from each other. And thus, they are identical. They could be assumed identical, right? It's one simple inference, okay? The same thing about the serial correlation coefficient. So first order serial correlation. Remember, when I'm correlating the times between to the first occurrences to the times between the second, third, and other occurrences. And again, my coefficient comes to be insignificant. My test statistic comes to be insignificant, thus showing the lack of correlation, right? So a lack of correlation synonymous to independence, right? If these two things are not correlated, it means that they're dependent. So therefore, by running these two tests, I am implicitly confirming the IID assumption independently and identically and independently distributed random variables, okay? And therefore, just computing these two numbers, I'm going back to my supplier and I'm saying that I'm sorry. In this case, I'm not going back to the supplier because it's a system-level problem, right? It's indicating that, hey, this particular failure, so it means that I'm going back to my Ford management, say, you know what? Let's stop this quarrel with the supplier. It's our fault. It's a system-level problem because you know, I can just looking at the data and computing the respective statistical measures, I can tell you, I don't know why engineering. See, this is what's called decision support for engineering, for further investigation. So that's the best we can do from the mathematical statistical side to support engineering, root cause analysis, and stuff like that. Okay? And then, of course, when I switch to the multiple repairable systems, now I have a luxury of actually constructing a distribution of time to first failure across all 6 million vehicles versus the distribution of time to the second failures between all six, and versus the time of the distribution from the second to the third failure. And I can construct distributions. So like in this case, you see, this would be the distribution, let's see, what's my notation here? This is my distribution of times to the first failure, and this is my distribution of the times to the second failure, right? I'm actually modifying the famous Kolmogorov-Smirnov test to give me a reliable inference whether or not these distributions are identical. Because if they are identical, right, then this distance is going to be close to zero, and therefore I will prove that they're identical, and vice versa if they're not identical. Okay. So once again, a quick numerical study. So this is a real data, of course masked in terms of the scale, but I'm looking. The solid line is the time to first failures, and the dashed line is the time. I'm sorry, not the time, but the CDF, the probability of failure corresponding to the first failures. It's the solid line, and the dashed line it's the probability corresponding to the times between the first and second failures. And in this case, since I'm interested primarily in this area because this is my warranty period, right? I can establish that there is enough. I can visualize that there is enough different enough separation, but I need to prove that statistically. So what I do, I use a special modification of the Monte Carlo technique, Professor Judy, I'm not sure if you used that before, called bootstrapping. So bootstrapping is basically drawing, it's a Monte Carlo-like, but I'm drawing from the empirical CDF as opposed to parametric CDF, right? And so by bootstrapping from the to CDFs, I'm constructing the distribution of the differences. I'm computing the distribution of the differences in this time section, T0, between these two distributions, and then looking at this distribution of differences. So this is my zero. So what do you say? Do they differ statistically, or they do not differ statistically? If this is the histogram of the differences between the two distributions.
No difference.
You say no difference?
Yeah.
I mean, look at this. This is 0. I mean, there's no difference. You have both negative differences because of randomness. You would have both negative differences and positive differences, right? This is primarily positive. You know, this. If I were, you know, to compute the area under the curve here, this is all to the greater than 0, right? It means that it gives me an indication that this difference is indeed statistically significant, and then it means that the respective logical conclusion is that the failures, this would be the indication of the failures of multiple siblings at different locations, i.e. a component level, not a system interaction problem. So this is where I could take it back to the supplier and convince them to pay us back for the all warranty repairs, or if you remember, it's called you know, warranty recovery process. So this would be a statistical backup. Yeah. Dollar value coming back. So, anyways, so this then concludes the discussion as far as the order and renewal process is concerned, i.e. when every time I replace the failed component and every time I'm repairing the system by as good as new, in other words, by brand new components. Question is, can I apply the same procedure? Can I apply the same procedure in the framework of
Two distribution is the first failure and time between first and the second failure.
So once again, once again,
inside,
good question, Professor. So first of all, let's look at the CDF first, right? The CDFs visibly show the difference, okay? But I'm not sure if this difference are enough to proclaim it to be statistically significant difference, okay? So then what I'm doing, and I'm interested, like I said, I'm interested in this period, in 40 months of service, which is approximately 36, 3 years in service, right? So therefore, I'm saying then that within, in other words, I'm zooming on this delta, and I'm trying to answer myself a question, whether or not, as of this time cross-section, these two distributions are different from each other. The reason I want to know if they're different,
interpretation is your first failure will be similar.
okay, let me
second failure.
yeah, yes, ma'am. So let me show why. Yeah. You probably forgot the actual problem formulation in the sense that the reason I would like to know that is that I would like coming back over here. Okay. So I would like to convince myself whether or not. So because you see that first CDF would characterize this interval, but from many realizations. And that second CDF would characterize this interval. I'm trying to convince myself whether or not these are identically distributed random variables. If they are identical distributed random variables, then my inference would be that they are coming, that this is a system interaction problem, because they are coming, this is the same part, and it gets superimposed itself on the common axis. As a
It's an exponential distribution, right?
No,
Even for
no.
single.
No, that's the case.
Yeah.
No, it doesn't have to. In fact, if it's exponential, then I'm helpless. Then I won't be able to distinguish because you see, with the exponential distribution, you see, I'm capitalizing on the fact that if the failures are coming from the same location, the superposition is going to be corresponding to IID. If they are not coming from the same location, the superposition is not an ID. However, if the underlying is exponential, then by Murphy's law, the superposition is still going to be as if it's coming from the same space. This exponential is a constant failure rate, and it doesn't matter where it fails. Therefore, at this level, I don't know. You know what I mean? So therefore, but the catch is that the renewal process, many people confuse the renewal process with the constant failure. It's not constant. It could be Weibull. It could be anything. The thing is that it has to be identical component. If the old component was suffering from increasing fatigue, then another component like this can also be suffering from increasing fatigue. You know what I mean? So, but anyways, so to just finish this discussion, we have about 10 minutes left. to finish the discussion here, why for practical purposes it's important. So we said that for the ordinary renewal process, we have a solution, and we can reliably resolve the dilemma, whether it's a system level or component level, in the framework of the brand new replacements. What if the replacements are not brand new? In fact, what if they do follow an HPP, non-homogeneous Poisson process? So every time you replace, it's almost like you have a failed spark plug which was 6 years old. You go to your garage, go to your shelf somewhere, and you have another spark plug which happens to be 6 years old from another car, and you just take that one and plug it back. You know what I mean? So then it's the same as old restoration, and the process then is an HPP. But similar how I rationalized you for the HPP, the constant failure exponential distribution approach, I can also mathematically prove that for me, unfortunately, the superposition of an HPP is yet another HPP, you see. You know what I mean? So therefore, if basically for practical, now if engineers come to me, my first question I ask, how do you replace your part? They say they come to you with the same dilemma. Sir, we don't know how to distinguish the system level or component level. I say, how do you replace your part? Do you replace with brand new or refurbished or same as old, etc.? They say brand new. Sure, I'll give you the answer. Same as old. Nope, sorry. Procedure doesn't work. Simply doesn't work. And the only other case would then be the so-called GRP process, the superposition of generalized renewal process. Remember when I said that it can be restored to anywhere between as brand new versus the same as old, okay? And that have that little Q factor, to which degree it restores, right? So the overall conclusion is basically formulated here. Under the GRP model, the closer the repair restores to sibling to as good as new condition, the easier it becomes to distinguish between scenario 1 and 2, i.e. between component level and system level. But if your restoration factor starts deviating towards the other end, the closer you get to the other asymptote, the more difficult it becomes to distinguish. So what we did a quick simulation where we said, okay, let's say we have 3 siblings, where for all of them we assume the underlying viable distribution with the shape parameter of 2 and scale parameter of 1, okay? But then, I'm sorry, for the shape parameter of 2, but the scale parameter of one of the 3 siblings is 1/3 relative to the remaining siblings. In other words, I am intentionally degrading one component in one location to see if the procedure will pick it up after the application. And also what's interesting, I'm applying this restoration factor equal to 0.5. I'm saying, okay, I'm neither as good as new, nor same as old, but somewhere in between. Will my procedure still be sensitive to pick it up? And again, the same thing. What I do, I compute the MCF as if it's coming from the ideal process versus the MCF when it comes from this modified process of 0.5. And again, I look at the differences. I look at the differences in the MCF. Okay. And what I observe is that, again, if I were to integrate, you see, like here, in the early exposure time, I won't be even able to differentiate. Why? Because with the low exposure time in the field, I don't even get to see enough repeat repairs for me to make any statistical statement. It's just barely one repair has only occurred. But as I extend my time, the difference between the two MCF, becomes primarily positive, consistently positive. It means that the difference is there. So therefore, my conclusion is this. This is to say that under this middle situation, so to speak, it would be possible, albeit marginally, to distinguish between scenarios 1 and 2. However, again, with Q increasing to 1 or decreasing to 0, it will become either more difficult or easier to make the contrast between the two scenarios. But the idea was to give yourself a comfortable feeling. So therefore, in this scenario of GRP, what I will first do, I will process this data first through the GRP model to give me the estimate of Q, and say, hey, if Q is like 0.15, I know it's pretty close to 0, right? It means that I will reliably be able to say. If the Q is 0.95, it's close to 1, I say, I wash my hands. I say, sorry guys. I mean, it was as much as I like this procedure that we invented, it will be helpless to establish the difference. Okay? So anyways, this slide is to show that we published it in the Wiley Journal. So this is the reference. You can always go to the website, and I think the Wiley downloads it for free. Okay, and you can read all the details about the paper for those who is interested. And here are some conclusions, but basically to say that engineering systems often contain identical components, the so-called siblings. When the field, i.e. warranty data, are analyzed, dilemma arises to how to interpret it. And from the standpoint of the root cause analysis, the task is to understand whether recurrent failures relates to system level or component level. And then basically summarizing that properly analyzed, in many cases, especially as good as new restoration, we can indeed give the answer. Okay? So I seem to be just on time to finish. Do we have any additional questions? Yes, sir.
So actually, you're basically comparing two distributions between the of the interval time, say that like the distribution of the first failure and the distribution of the second failure.
Yes.
But is there a chance? Because you also mentioned the Weibull distribution. So is there any chance like you first model the interval time using the Weibull model, and then you just monitor the parameters? In that way, you can online monitoring all the parameters to see whether the shape parameter or the scale parameter change. In that way,
I see. So you're saying that, let's say the time to the first failure distribution is viable with certain parameters, and then the second, the time between this first and the second is viable with different parameters. Yeah, I could do the test for there is another test for the equality of the shape parameters versus the equality of the location. In most cases, if this is one and the same failure mode, the shape parameter happens to be very similar. So therefore, the so-called failure mode conservation principles, where if you imagine the Weibull plot, the slopes of two Weibulls are going to be similar. However, you can measure the difference in the location parameters using, for example, chi-square test, and then convince yourself, yes, you can do that. The only reason I did this non-parametrically is because I didn't want to assume another layer of uncertainty by fitting a parametric distribution into this one. Usually I fit the distribution when I need extrapolation. In this case, I didn't need any extrapolation. I just needed a fixed time section and to compare the two CDFs. But yeah, what you are saying is, yeah, by relying on the difference between the location parameters, you can establish whether they are different or not.
Once you get a good estimate of the shape parameter and scale parameter, you can also compare the distributions by using like KL divergence or something like the distribution, distribution.
There's tons of methods. Exactly. There's many methods that if you need to establish the, I think within the even within the Kolmogorov-Smirnov family of tests, there is a test that compares to CDFs, but based on dispersion, something of that nature. Yes. Okay. Any other questions?
So just based on your
Yes.
results, very interesting. I think it's very useful in reality. But do you give recommendation to the people like, later on when you try to do repair, in order to easy to separate a system failure or component failure, you must replace as in the new part rather than you use your load, your Q, right? So
I see what you're saying.
So that might be easier to make a reliable decision. So from
You mean at the time of the repair?
Yeah.
Well, first of all, so I see what you're saying. You are saying, okay, if this spark plug fails for the third time, you're not sure why it's failing. But you can do a statistical analysis and say, you know what, at this point, replace the entire stinking engine. Because it's not the spark plug, it's the engine that stresses it out and then respectively, causes the failure. Yeah, that's a good one, but no, we haven't tried it in real time because we use this as a decision-making support in root cause investigation. So why is it failing? So, but to do it on real time, I think you would need to have quite.
More like a small size just for your validation of your conclusions for that. So it's more like your fault. Want to say, it's really I have system failures, right? Or I have component failure. Now you tell them I have component
No,
failure.
but that's exactly what they do. Once we provide these clues to them, they start diving in, and they either, for example, I mean, I had 2 or 3 case studies in the so-called spike recovery process, where we indeed connected the supplier. They reluctantly accepted the result. They didn't want to believe it. But when they went to their production process, etc., they indeed found 2 what do you call it, shifts, 2 consecutive shifts, when the manufacturing condition, that one of the parameters was off of the range, and they say, yeah, sorry, yeah, there is indeed, this population that we released. Yeah, no, but at least that helped. And there might be cases where, you see, I mean, once we computerize the system, I'm not even aware of all the cases they're using them in. You know what I mean? It just gives them the red versus green flag, and then engineering dives it in. Yep. So. Okay, guys. I think you're hungry. Your pizza is here. As I was a student, I was always hungry. Therefore, I'm not going to be depriving you from the pizza lunch. Again, thank you for attention. The idea of this seminar, jointly with Professor Judy, was to give you guys a flavor that whatever you are studying here in the school can be meaningfully applied in the industry. It's actually, so you are studying those convolution integrals, not just for the sake of exercising mathematics. They actually work, and they help you to design better systems, better world, and so therefore your time is not wasted here. Plus, we get paid pretty well, trust me, in the industry. Thank you.